Hi guys, Mrs. H here. Today we're going to be looking at chemical equations and chemical reactions. So at the end of this, you're going to be able to look at and understand the words and the chemical formulas used to express a chemical reaction and also how to balance these chemical reactions. And again, notice we have some vocabulary here as well. So, describing a chemical reaction. So, chemical reactions occur when we get a new substance form. So, I'm going to take hydrogen and I'm going to take oxygen and I'm going to chemically have a reaction. So, we're going to change the physical properties of the substance and I'm going to get something new. I'm going to get a compound like water. So, whatever I started with, we call the reactants. Those are our ingredients. And whatever I end up with, that's what we call our products. Another way I like to think of this is think of baking a cake, right? Baking a cake is a chemical reaction. I start with flour and sugar and all our list of ingredients up at the top of the directions. And I mix them all together and then I put them in the oven and I bake, right? I make a cake. So my ingredients are my reactants, and the final product, my cake, is, again, notice the word I said, product, right? So that's the words that we use to describe chemical reactions. We use the words reactants and products, what you start with, what you end with. And remember, what you started with and what you end with will have different physical properties. And the reason why they will have different physical properties is because it's new material. I'm taking my oxygen that I breathe in and taking the hydrogen and I'm going to get, again, here's my water, right? And it's a new chemical makeup and it's going to have new chemical and physical properties. So in order to save time, and it's easier to do it this way, we write this in a chemical formula, and it's just a summary or a description of what's happening on a molecular level. So again, when we write this on the on the left side is your reactants, and then we use this arrow, and that's yields, and then the right side is the products. So anything you start with, go on the left side of the equation. Then you do a yield sign, and that means I'm going to make, I'm going to change into, I'm going to produce, I'm going to end up with. And what do we end up with? That's the reactants, and that goes on the right side of the chemical equation. And again, this is just a quick shorthand expression of what's happening to the atoms and how they're rearranging themselves. And so sometimes we have more than one reactant, and actually sometimes we have more than one product. So how do we differentiate that? Well, we use this plus sign. Just like in math, you're adding to. So I'm going to add reactant 1 to add reactant 2. I'm going to add my oxygen. I'm going to add my hydrogen. And we're going to add them together, or they're going to, hydrogen and oxygen are going to react with each other, right? And so what does it yield? What does it produce? That water. And again, on the product side, we use the word and. So the plus side can be and as well. So we say reacts with or and, so that we can understand verbally how we say the chemical equation with the expression of the chemical reaction or a chemical equation. So here I have multiple reactants and multiple products. So how would we say this? I would say reactant 1 and reactant 2 yields product 1 and product 2. I could also say reactant 1 reacts with reactant 2 and makes product 1 and product 2. Again, notice it's just a little difference in wording, but it still means the same thing, but just a little difference, a little variation. So word equations, when we actually write the name out, we don't really use it very often because, again, we're doing the chemical equation because we want to save ink and we want to save time. But sometimes we do use the full names. And so here would be an example. Magnesium reacts with oxygen to produce magnesium oxide. I could say magnesium and oxygen react together to make magnesium oxide. Again, my words, just a few little changes, but the meaning didn't change. Just like calling me Mrs. H and calling me Mrs. Helbing is still the same thing, just a little variation, same meaning. Okay, so let's do a quick review. See if you can answer these 3 questions. Okay, was it kind of hard? Could you think of it in your head how it would look? Well, let's try them out. So here I have hydrogen reacts with oxygen to form water. So how would this look in the full name written out? I would say hydrogen with the plus sign, oxygen, and then the arrow with water. And so again, how would I say this? Hydrogen and oxygen react to form water. Notice again, my reactants are on my left side and my products are on my right side. Notice we use the little arrow to mean yields or reacts with, and then the plus sign meaning adding or what we're putting together. So let's try another one. So I have sodium reacts with hydrochloric acid to form sodium chloride and hydrogen. So sodium plus hydrochloric acid. Notice the arrow to represent yields. Yields or produces sodium chloride plus hydrogen. Again, notice the reactants are on the left side and the products are on the right side. Also notice we're separating the reactants and products is the little arrow, and then the plus signs to separate the 2 products from the 2 reactants. And then our last one, copper oxide reacts with carbon to form copper and carbon dioxide. Notice I have copper oxide plus carbon yields copper plus carbon dioxide. So again, notice my reactants are on my left side, my products are on the right side. Notice they're separated by the yield sign, the arrow, and then separating the 2 reactants is a plus sign, and separating my 2 products is also a plus sign. Writing the words is not necessarily the most efficient. And again, the idea is writing out chemical equations is a shorthand. It's quick. It's an annotation. So we would use the chemical formulas in place of these words. So if you notice, these were some of the reactions that we did before. We said water, hydrochloric acid, carbon dioxide, sodium chloride, sodium hydroxide. So instead of writing out the full name, we can actually replace the full name with the chemical formula. And so this is actually the easiest shorthand way to summarize the chemical reaction that's occurring. So let's go ahead and look at that with the chemical reactions. So again, here are the 2 reactions. Hydrochloric acid and sodium hydroxide gives or produces sodium chloride and water. And then coal, which is carbon, reacts with oxygen gas to produce to produce carbon dioxide. So what would those 2 reactions look like if I would do it in shorthand? So hydrochloric acid, that's HCl, and sodium hydroxide is NaOH. So notice the and we've replaced with the plus sign, and gives, remember gives means produce, so I need to have a yield. So then sodium chloride is NaCl, and with our plus sign, water, H2O. So HCl plus NaOH yields NaCl plus H2O. So that's how you would write that out. And that's what it means. Hydrochloric acid and sodium hydroxide produces salt and water. Okay, that's the chemical reaction that we just did. Notice, a lot simpler to write. Shorthand, there's a lot of writing going on here. So this is just the chemist's shorthand. They're lazy. They don't want to write it all out. So they write it in shorthand. So let's look at the other one. So we have carbon, C, plus oxygen, which is O2, produces, so we need our yield sign, carbon dioxide. So that would be CO2. So C plus O2 yields CO2. Much easier, right? Look at how long that sentence was. Look at how short this sentence is. Much easier to write. So now we're not finished with just writing the chemical equation because of the law of conservation of mass. So the law of conservation of mass basically says, not basically, it does, there's no basic about it. It states that matter can't be created or destroyed. As much as magicians like to pretend like they can pull a rabbit out of a magic hat and it appears out of nowhere, that's not true. They're tricking your brain, right? They're illusionists. It's a trick. That rabbit wasn't created. It came from somewhere. So atoms can't be created or destroyed. So they have to come from somewhere. This is called the law of conservation of mass. That's what we call it. So when we write our chemical equations, we need to make sure that we're showing that we are not destroying matter and we're not creating matter. And so what we do is we balance equations to show that. And so let's go ahead and look at that. So there's been some theories to prove this. So if you weighed all the ingredients that you had before you baked your cake and then bake your cake, rebake your, I can't speak. If you weigh all of your mass from your ingredients and then weigh your product, the cake, they're going to weigh the exact same. Now you have to also remember some things are gases and become a gas, but you'd have to weigh that as well. And they wouldn't weigh the exact same. Now, when you get into chemistry class, you will experience that. You will do chemical reactions where you actually demonstrate the law of conservation of mass, that what you started with is what you end with. So how do we do that? So in order to do this, we need to put coefficients. So the coefficient, remember, tells us the number of molecules we have of that substance. So by putting a coefficient in front of our compounds or in front of our molecules, we can represent how many of those we need. So like it's saying, I need 2 bags of cheese, right? I need 2 cups of water. The cups tells you how much water you need. The coefficient tells you how much you need. How many molecules do you need in order for this to happen? Because as we all know, if you don't add enough sugar to your Kool-Aid, it tastes terrible and it's not Kool-Aid. You all know if you screw up your measurements in baking a cake, the cake is going to taste terrible, right? So how much the quantity matters. Your coefficient in front of your molecules tells you how much. So let's look at this. Notice this diagram. I have 1C, here's your carbon with 1, 2, 3, 4. So this is a model to represent methane. So here's our molecule, CH4. Notice that I need 2 oxygens, 2 oxygens that are 2 oxygens together, and it's going to make 1 CO2, which has 1 carbon and 2 oxygens and 2 water molecules. 1 molecule with an excuse me, an oxygen and oxygen and hydrogens here, and an oxygen and hydrogen here. So let's look at this. The carbon is C, and that's that black dot. Notice there's 1 black molecule on each side. Notice there's 1, 2, 3, 4 white molecules, 4 hydrogens, and 1, 2, 3, 4 hydrogens on both sides of the equation. So then lastly, notice there's 1, 2, 3, 4 O's or 4 oxygens on the reactant side. So I have 1, 2, 3, 4 oxygens on the product side. So in order for me to have 1 methane plus 2 oxygen will produce 1 carbon dioxide and 2 water molecules. That's the only way this molecule will work. If I don't have enough oxygens, I'm not going to be able to make my water molecules. If I don't have enough hydrogen, where's the, so it has to be balanced. Where are these hydrogens going to go if there's not enough oxygens, right? They'll have no place to go. So we need to make sure we have enough oxygen over here. so that my hydrogens, when there's the chemical reaction, has a place to go. Otherwise, you won't be making carbon dioxide and water. You would have something different that you would be making. So the law of conservation of mass says that I need to balance my equations. So the number of atoms on my reactant side must be equal to the number of atoms on my product side. They must be the same number and the same kind. So let's look at this example. So here I have H2O2 yields water. So I have 2 hydrogens over here, and I have 2 hydrogens over here. But what about this one oxygen? There's still an oxygen there's 2 oxygens over here and only 1. So where's this oxygen right here going to go? So this is not a balanced equation, because where's the hydrogen or where's the oxygen? It's not accounted for. So again, we need to add the coefficients so that we can properly express our chemical reaction. So again, let's look at what we had. Whoops, sorry. Well, a little crazy here. So let's look at what we had. I have a total of 4 hydrogen here, a total of 2 oxygen here. So a total of 4 atoms, 2 hydrogen, 1 oxygen, so a total of 3. Not balanced. So what can I do? I can add coefficients in front. I don't want to change the subscript. If I change the subscript, I'm changing the substance that I have. It's something new. It's a new substance. So I have to keep these the same. Don't change it. So let's look at how we do this. So remember, product side, this is what we had. Reactant side, this is what we had. So hydrogens are balanced, but our oxygens are not, and our total number are not. So we have to fix that. So how can we do this? Well, notice right here, excuse me, my hydrogen said it was balanced, but my oxygen is not. So I have 2 oxygen right here. So I need to have 2 oxygens over here. So what can I do? I can add a 2 in front of my water, in front of my H2O. So what does that do? Well, then I will have hydrogens 2. What happened to my hydrogens? I now have 2 times 2, that's 4. So now my hydrogen's not balanced. So in balancing my oxygen, my hydrogen became unbalanced and my total numbers are not right. So we're not finished. I got to keep going. So what can I do? Well, remember, oxygens are okay, but how many hydrogen do I have over here? I have 4. So what can I do to make 4 hydrogen over here? I can put a 2, because 2 times 2 equals 4 hydrogens. So this allows me to have 4 hydrogens in front, or total, in the reactant side. So now let's look. I have 2 times 2 equals 4. That's good. Over here, 2 times 2, that equals 4. Check. Oxygen, 2, 2, 2, 2. That's good. So let's look at my total. So I have 4 and 2, that's 6. Okay, 4 and 2, that's 6. So notice my reaction is now balanced. So let's try another one. Let's try another one. Let's look at this visually, how this would look. So here I have my 2, notice 2H2 plus 1O2 yields 2H2O. Notice I have 1, 2, 3, 4 hydrogens. 1, 2, 3, 4 hydrogens. How many oxygens? 1, 2, 1, 2. Total of 6. Total of 6. Thumbs up. It's all set. So here are some practices that I want you to do and try out for yourself and see how you do. Okay, if you have any questions or need help with these, please make sure you reach out to me. Second part, or another part of chemical reactions is identifying the types of chemical reactions. So here's some core vocabulary. Some of this we will look at more closely than others. So let's go ahead and get started. There are several different types of characteristics that we see with chemical reactions. synthesis, decomposition, combustion, single displacement. Sometimes use the word replacement instead. Double displacement or replacement, and acid-base neutralization. Acid-base neutralization is something that's looked more closely in an advanced chemistry class, but we'll go ahead and look at what it is. So the first kind is synthesis. So synthesis is also when you synthesize means to make. So you're making something. So you're taking a smaller molecule and making it into a bigger molecule. So if we had two elements and we actually bind the two elements together to make it a bigger one, that would be a synthesis reaction. So our reactants are small and our products are big. So a couple of examples is taking sodium and chloride and putting those together to make salt. Another one is taking silver and adding it with sulfur and making tarnish, which would be silver sulfide. And then also when we make rust, that's taking iron and oxygen. And then the last one would be photosynthesis. So if we take the sunlight and carbon dioxide and water, and we combine those to make sugar and glucose. So these would be all synthesis. So we're starting with a small particle and making it bigger. Now remember, it's relative, because I could start out with a relatively big compound and make it even bigger. It'd still be considered synthesis. Now the opposite of synthesis would be decomposition. Decomposition is when we're breaking down the reactants. So I'm taking something big and making it smaller. These can be done in one simple step, or sometimes we have multiple steps in making this. So decomposition, usually we have some kind of heat added when we have decomposition, but not necessarily. If you have a compost pile, you'll notice that the compost actually, when you open it up, the bin, you can actually see the heat and see the steam from the reaction occurring. Sometimes we need acidity to initiate the reaction, or humidity, or even electricity to get these decomposition reactions to go. So decomposition that requires heat would be thermal decomposition. Electrolytic decompositions, we would need the electrical current, or even a catalytic decomposition where you need a catalyst, or you need to add something to get the reaction to go without it really participating in the reaction. It just kind of gets things moving. So if we look at decomposition, we're looking at a compound and breaking that compound down. Again, we can start out with a really big molecule and make it just smaller, or a kind of small one and make it really small. It just depends on what kind of decomposition reaction we have. So examples here would be taking hydrogen peroxide. And actually for this to happen, we would need electricity. And so we can break it down to water and oxygen. Electrolysis of water, again, needing electricity. You can take water and break it down into hydrogen and oxygen, and then actually taking potassium chloride and breaking it down into potassium and chlorine. So again, starting with a big reactant, and our products are small. Fermentation is actually very common, well-known decomposition. So fermentation would be the opposite of photosynthesis, where we're taking the sugar and actually breaking it down into smaller parts. So fermentation, again, is used when we're making breads and beers and the like. And so again, we need yeast typically as our catalyst. And so we're taking a big compound and making it smaller. So go ahead and look at these and see if you can identify these as synthesis or decomposition. So how'd you do? The first one is synthesis, because we have too small, making it a big. Number two, again, is decomposition, because we're making it big and making it small. Three is decomposition, because we have a big compound making it small. And number four, we have two small compounds and making a bigger compound. So the next type of chemical reaction is combustion. This is usually when you hear the word burning. This is associated with combustion. And so we're taking hydrocarbons, which it is what it says. It has a hydrogen and has carbon in it. And what are we doing? We're making carbon dioxide and water, and oftentimes heat. Combustion reactions do release heat, and there's a change in temperature. And sometimes that change in temperature isn't really noticeable, and sometimes it's very noticeable. Also to note here, in order for a combustion reactions to occur, we also need oxygen. So again, we're taking the hydrocarbon. Notice I have a carbon and a hydrogen, and then I'm adding oxygen to it. Combustion reactions won't occur without oxygen, and I'm breaking it down into a carbon and water compound. Combustion reactions will always have carbon dioxide and water as their products. Now, sometimes you'll have like what we'd call soot, or we'd have extra. And if that happens, we're actually looking at the difference between complete combustion reaction and incomplete combustion reaction. So if we're looking at these, notice we have the hydrocarbon and an oxygen. Notice the reactants are always carbon dioxide, water, and heat. So now, again, the difference between complete and incomplete. Complete, it's 100% efficient because there's no limiting reactant. So all of the products are going to become carbon dioxide and water. But if I can't, like if I have extras, so imagine you're going to the store and you only need one part of the kit, so you have extra of part of the kit left over. That's kind of what's happening with incomplete. You don't use all of the hydrocarbon. And so complete combustion is usually considered what is clean. So when you hear clean energy or clean combustion, that's often what they're talking about. So burning candles, that would be an example of a hydrocarbon that reacts with oxygen. And again, all we're producing is carbon dioxide and water. If you ever see a candle where it actually has like a black smoke to it, then this is, again, would not be a clean. This would be, or would not be complete. This would be incomplete. So this is when you get that soot and that gross burn. Burning coal is an incomplete. That's why you get soot. If you've ever seen the movies where the coal miners come out of the coal and they're all gross, whatever. Well, one, coal is all that dark nastiness. But what else do you see in the coal burning facilities? You see the smokestack, and the smokestack is really like that disgusting, yucky stuff. That's because it's an incomplete process. So again, let's take a look at these examples. Can you identify complete and incomplete? How'd you do? I'll be honest, this isn't really critical in identifying combustion as complete or incomplete. I won't have that on the test, but I do want you to be aware of the difference because you hear a lot of conversation in the media about having clean combustion. Okay, so single replacement sometimes are known as a single displacement. So notice we have an element and a compound. And what will happen is the element is going to bump out one of the elements in the compound and replace it. It's going to displace it. It sounds exactly what it sounds like. Almost all acid metal reactions are a single replacement. So what are you having? You have a metal and you have an acid, and they're replacing acid metal reaction. Okay, so where you're exchanging one ion for another ion. Why would this happen? Well, it's a better arrangement, or it's a better electron configuration, and so that's why this is happening. There is a scale to know whether or not a single replacement would happen. That's something that you would look at in an advanced chemistry class, but here we're just identifying what a single replacement would look like. So in general, we see the A element plus BC yields AC plus B. And so this is kind of our general write-up or our generic form for a single replacement. The one thing you need to note is if A is going to replace B, they have to both be the metal. So I can't put in a non-metal to replace B if B is also is a metal. So the reaction is you're replacing one ion with another ion, okay? So here's some examples. So I have magnesium and hydrochloric acid. And so the magnesium kicks out the hydrogen, and so you get magnesium chloride because that's a better electron configuration. The next one we have silver nitrate and zinc. So zinc is going to kick out the silver, and so you're going to get zinc nitrate. And again, why does this happen? Because the zinc with the nitrate is a better electron configuration. So can you identify these as synthesis, decomposition, combustion, or single replacement? So how'd you do? So on the first one, notice we have the calcium being replaced, or sorry, the chlorine replacing the iodine. So again, notice it's the nonmetal replacing the nonmetal. So this is a single replacement. On number 2, it's decomposition because you're starting out with something big and you're breaking it down. Number 3, you're starting with something small, making it big, so therefore it's synthesis. And then the last one, you're seeing carbon and water in your products, so you know it's going to be a combustion. So another one we need to look at is double replacement. So double replacement is you're actually going to have 2 compounds and you're going to flip-flop the arrangement of the 2 compounds. Most commonly occur in ionic compounds. Sometimes you do see acid and bases in a double replacement, but more often than not, these are ionic compounds. And usually the solvent for this type is water. So we're having an exchange of these 2 things where you're having an ionic compound. So if we look again at that generic write-up, we have compound AB with compound CD, and notice the metals are the ones that are exchanging locations. So I'm not going to flip a metal and a non-metal. I'm flipping one metal and another metal to make 2 new compounds, flipping what metal is with the non-metal. So in general, we say A and C flip positions or switch positions. There also the states of matter are usually given. So we would say, okay, this is a participant, or there's a particulate, or this is aqueous. So in these, we usually will have an identification of what state of matter they're in when we have a double replacement. So here we have some examples. So notice on the first one, the hydrogen and the iron are flip-flopping because or iron chloride is a better arrangement than the hydrochloric acid. And then we're also getting water with it. So the second one, again, we have notice the silver and the sodium. We have salt and we have silver and nitrate. And so again, the sodium and the silver are flip-flopping positions to form 2 new compounds. And then the last one we see here, this is when we were talking about earlier, with having those symbols, AQ would be aqueous and S would be solid. So you have 2 liquids that are being mixed together, and what will end up happening is you're going to get a precipitation in this liquid when these 2 this reaction, this double replacement reaction occurs. So can you identify the difference between a single replacement and a double replacement? Let's see how you can do. So how'd you do? So on 1 and 3, notice there's an element with a compound, so we know those are going to be single replacements. But on 2 and 4, notice we have 2 compounds, so we know we have a double replacement or double displacement. So the last type of reaction is an acid-base reaction. And so the big thing we're having here is we have a hydrogen ion in one compound and an OH compound in another. So again, if you notice right here, here's my H, so some kind of acid typically. So we have an H over here with a nonmetal, and over here, notice we have an OH. And so what do we have? HOH, it's going to become water. And so this would be an acid-base or neutralization reaction. So types of acids used in the reaction determine the ion that's going to be in the salt. And so I just wanted you to kind of see what's going on here. So notice here's my acids, and notice at the beginning you have this H, and so this H is actually going to be popped off of that compound. And we can really see the H's here really stand out. And so the H pops off so that it can produce water. So here are some examples. Again, I will not be testing you on identifying the acid-base reaction, but I wanted you to notice here's your H, here's your OH, here's your H, right here, here's your OH. And so again, you're looking for an H and an OH in your compounds. So a lot of times these look like a double replacement, but it's a very specific type of double replacement. It's a double replacement that has water as the end product. So it's kind of a way of thinking of that. And so one of a common reaction that you see is that vinegar and baking soda. And so the vinegar and baking soda reaction is actually an acid-base reaction. And there's actually a flow chart here to help you figure out what kind of reaction is occurring. So if you're struggling on, okay, what kind of reaction is this? Here's this little flow chart to help you figure out what kind of reaction is occurring. So let's do one final run through to see how you do. So how'd you do? I hope you have a good understanding of what the different types of reactions are after this, and also the whole idea of conservation of matter and how we can balance these reactions as well. So if you have any questions, please make sure you're reaching out to me. Bye, guys.